This is the video on the Unit 5, Section 1 Notes Part 2 regarding the early gas laws, both what they are and how you would solve problems involving them. Overall, we'll talk about Boyle's Law, Charles' Law, Gay-Lussac's Law, and also Avogadro's Law, although we won't actually use Avogadro's Law mathematically in this class. So first, let's talk about Boyle's Law. What Boyle's Law is our pressure-volume relationship. Basically, what it says is that if you keep the amount of gas N constant and the temperature constant, then the product of pressure and volume will also be constant. Or, as we've talked about before, as volume goes down, pressure will increase. As far as calculations go, the product of an initial pressure times an initial volume, P1 and V1, is equal to the final pressure times the final volume. So we can use this to predict final conditions based on initial conditions. How this law might be viewed is if you take a gas, say in this kind of dash pot here, at a certain pressure and a certain volume, if you squeeze that gas into half the volume, as we can see down here, the volume is halved, the pressure will double. Now we can actually predict these amounts mathematically if we know the initial pressure and volume and one of these final conditions, pressure or volume. Let's take a look at how that goes. So in our first situation, we have a piston in a car engine with an initial volume of 0.50 liters, and that is filled with gas vapors at an initial pressure of 3.7 atmospheres. After the piston compresses that gas to a new, smaller volume of 0.15 liters, what is the new or final pressure of the gas? So let's first arrange the different pieces of information we know. We do know the initial pressure. We do know the initial volume. We don't know the initial pressure or the final pressure. That's what we're looking for. And we do know the final volume. Let's plug in what we know. The initial pressure is 3.7 atmospheres. The initial volume is 0.50 liters. The final pressure we don't know. That's what we're looking for. And the final volume is 0.15 liters. The way we would solve this problem is we'd first start by rewriting Boyle's Law. We then plug in the values that we know. Because we're looking for P2, we want to leave that as P2, the final pressure. Now, algebraically, the way I'm going to tackle this is I'm actually going to use reciprocal fractions, and I'll show you what that means. On the right side, we need to cancel out this 0.15 liters. So I'll actually set this up as a fraction, put it over 1, and multiply so that that 0.15 liters cancels. So we'll need it in the denominator in my algebra so that it cancels with the numerator in my Boyle's Law. Now, what I do on the right side, I have to do on the left. That's just algebra. So set up the left side exactly the same way. Notice that the numbers don't cancel here, but liters, that unit of liters, will. Now I'll rewrite the problem with everything that's been canceled gone. In my new numerator on the left, I have 1 times 3.7 times 0.50. So that's just 3.7 times 0.50. And in the denominator, we have 0.15. Notice the only unit left over is atmospheres, which should make sense because we're looking for a pressure. And on the right side, the only thing that's left is just my P2, which is what I'm looking for. Afterwards, we'll do 3.7 times 0.50 divided by 0.15. And so we have 12.33, and the only unit remaining is atmospheres, and that's equal to our final pressure. And we can kind of check this logically. Volume decreased, and pressure went from 3.7 to 2.33, so pressure increased. So this is logical. Let's take a look at a second example that is slightly different, requires one more step. In my second Boyle's Law calculation, we have a fixed quantity of gas at 23.0 degrees Celsius, and it has a pressure of 748 millimeters of mercury. And it's going to occupy a volume of 10.3 liters. So those are our initial conditions. The problem asks us to calculate the final volume if the pressure increases to 1.88 atmospheres, but the temperature remains the same. Let's set up our problem the same way. Pressure, volume, temperature to start, and pressure, volume, temperature to end. You'll notice that I included temperature here, even though Boyle's Law doesn't actually involve temperature. Let's plug in what we know. We know the initial pressure is 748 millimeters of mercury. The initial volume is 10.3 liters. And the initial temperature is 23.0 degrees Celsius. The final pressure is 1.88 atmospheres. The final volume, we don't know. That's what we're looking for. And that final temperature is also 23.0 degrees Celsius. It didn't change. It said the temperature remains constant. So in this problem, we have to make a few changes to start. First, notice that temperature doesn't actually matter in Boyle's law. If it remains constant, we can essentially ignore it. We also have to change our pressure to the correct units of atmospheres. We'll do that right here. Start with the pressure you're given over 1. Multiply by your conversion factor. 1 atmosphere is equal to 760 millimeters of mercury. The units of millimeters of mercury will cancel, and we'll be left with 748 over 760 ATM, or 0.98 atmospheres of pressure. Now let's do the problem itself. With our new pressure, we'll set up Boyle's law, plug in the pieces we know, change this side to a fraction, and multiply by the piece that needs to cancel out. It will then cancel. What we do on the right, we have to do on the left. So we'll set up our algebra in red again. The unit of ATM cancels, but the numbers don't. Multiply across numerators and denominators, and you'll end up at this term right here with liters as our unit. And once we multiply numerator and divide by 1.88, we'll get 5.37 liters as our final volume. And this should make sense. Pressure went up, and therefore volume decreased from 10.3 to 5.37 liters. And that's Boyle's law. Now let's look at Charles' law. Charles' law is a slightly different law. We no longer care about pressure here. What Charles' law is our temperature-volume relationship. This says that if the amount of gas and the pressure are constant, then the temperature and the volume are directly proportional. Or in other words, as temperature increases, volume will increase as well. For use in calculations, we have this equation down at the bottom. Initial volume divided by initial temperature is equal to final volume divided by final temperature. The situation of Charles' law really applies when we have some kind of container that has a gas where the container can change its shape or change its size. You're thinking tires or balloons or some kind of rubber. For instance, tires are going to deflate in winter because of Charles' law. The temperature decreases and the volume decreases as well. Now, quick note, because we're now dealing with temperature, we always need our temperature in Kelvin. And the way we'll get to Kelvin is we'll take our temperature in Celsius and add 273. So now let's do a Charles' law calculation. In Charles' law, we're going to start this one by saying we have a fixed quantity of gas at 23 degrees Celsius and a pressure of 748 millimeters of mercury. This may sound familiar from our last problem. The volume of this gas starts at 10.3 liters. Now, if the temperature rises to 165 degrees Celsius, the problem's asking what will the new volume be when the gas pressure remains constant. Let's do the same thing we did before. We'll list what we know. Here's all our variables. Pressure 1 is 748 millimeters of mercury. Volume 1 is 10.3 liters. Temperature 1 is 23 degrees Celsius. Pressure 2, the pressure is constant, so it doesn't change. It's still 748 millimeters of mercury. Volume, final volume is what we're looking for. And final temperature is 165 degrees Celsius. Now notice that pressure doesn't change. We don't have to concern ourselves with pressure if it's the same. Also notice that our temperatures are in degrees Celsius. To convert them to Kelvin, just add 273 to get them into Kelvin. And we've done both of that. We've done that for both of them on this slide. Now we'll rewrite our original temperatures and actually do Charles' law. Start by writing Charles' law, then plugging in the pieces you know, leaving V2 the same as it was. Now to get this V2 by itself, we'll multiply by 438 Kelvin over 1 on both sides so that it cancels on the right, and on the left, Kelvin will cancel. We'll do our multiplication on the left, 438 times 10.3 over 1 times 296. We have that down here. And once we do our math, we'll find that we have 15.24 liters as our final volume. That should make sense. Temperature went up, and volume also went up. In our second calculation, we're saying our classmates having a party, and we've got balloons with a volume of 2 liters, and they're held in a hot room at 297 Kelvin. During that party, someone puts a balloon in the freezer, and the volume shrinks, but the pressure stays the same. And we want to know what's the temperature of that frozen balloon. We'll list all our variables. We know the initial pressure is 1 atmosphere. The initial volume is 2 liters. The initial temperature is 297 Kelvin. Final pressure stays at 1 atmosphere, it's constant. Final volume is 1.78 liters. And final temperature is unknown, that's what we're looking for. So we don't have to pay attention to pressure because it's constant. We'll set up our Charles law and plug in. Now notice the piece we're looking for, this T2, is in the denominator. We have to get that out of the denominator. A quick trick you can use if you have fractions on both sides, if the entire equation is fractions, is you can actually just flip every fraction. Notice that the left and the right sides, I just flipped them. Now I can do the same thing I did before. Multiply both sides by whatever needs to be canceled. On the right, that's 1.78 liters. And on the left, we have to do the same thing, 1.78 liters. On the left, only the units of liters will cancel. We'll rewrite our math, and we'll find that our final temperature is 264.33 Kelvin. Remember that we can use this flip trick, shown here, if our term is in the denominator. Now, our last law that we're going to look at mathematically is our Gay-Lussac's law. Gay-Lussac's law is very similar to Charles' law, but it relates temperature and pressure. It says that if we have a constant number of gas particles and volume, the temperature is proportional to pressure. As temperature goes up, pressure goes up as well. For this law, temperature must also be in Kelvin. And for use in calculations, we'll see it looks very similar to Charles' law, but instead of volume, we're talking about pressure. An example of this would be a pressure cooker. As you turn on your pressure cooker, the temperature increases, and so does the pressure inside that cooker. A quick calculation of Gay-Lussac's law. If we have an aerosol can that has a pressure of 1.2 atmospheres at 298 Kelvin and someone throws that can in a fire, what will the final gas pressure be when the temperature reaches 1201 Kelvin? We'll list what we know to start: our initial pressure volume temperature, our final pressure volume temperature. Our first pressure is 1.02 atmospheres. Our first temperature is 298 Kelvin. Notice that volume is not mentioned. Our final pressure is unknown, that's what we're going to calculate. Our final temperature is 1201 Kelvin. And it becomes clear that we can ignore volume, it wasn't even mentioned. And Gay-Lussac's law doesn't involve volume. We'll rewrite Gay-Lussac's law, plug in the pieces that we know, get P2 by itself by multiplying by 1201K on the right and on the left because of algebra. We'll cancel out 1201K on the right, getting P2 by itself, and just Kelvin on the left. We'll rewrite our math on the left and just P2 on the right side. And our final pressure is 4.11 atmospheres. And this should make sense. Temperature increased, and so did pressure. Now, we do have one more law that I want to discuss briefly, and that's Avogadro's law. Avogadro's law says that if you have an equal volume of gas, same temperature and pressure, you're going to have the same number of gas particles. And this is what we used in an earlier unit. We say that at standard temperature and pressure, so 273 Kelvin and 1 atmosphere, if you have 1 mole of any gas, it's going to take up 22.4 liters of space. And you'll know, as we said before, 1 mole is equal to this many particles, an Avogadro's number of particles. Now, this is true for ideal gases. In reality, this equation doesn't quite hold, but it's good for a large variety of gases. And we can see the equation here. As number of particles goes up, volume goes up. The equation ends up looking very similar to Charles and Gay-Lussac's laws. Now, what situation would this be similar to? Well, this is kind of like when you inflate, say, a balloon or a tire. You're putting more gas in that vessel, and it's becoming larger and larger. Here's a quick summary of all the laws we talked about in this presentation. I hope this helps you understand what these gas laws are and how to solve problems involving them.